But we're talking about Gordon Gould today. Now, Gordon Gould was an American physicist who's often credited with the invention of the laser, a laser literally being the laser beam. He's best known for his third-year flight with the United 30-year fight. Third-year flight. Don't ask. I've got to clean my glasses. That's what I should do. 30-year fight with the United States Patent and Trademark Office to obtain patents for the laser in 1957. Many scientists, including Townes, were looking for a way to achieve a maser-like amplification of visible light. In November of that year, he found a viable way of creating a narrow, intense beam. Gould recorded the analysis and suggested applications in laboratory notebooks under the heading "Some Rough Calculations on the Feasibility of a Laser Light Amplification by Stimulated Emission of Radiation." Unfortunately for Gould, the government declared the project classified, which meant that security clearance was required to work on it. Because of his former participation in communist activities, wow, I didn't know that, Gould was unable to obtain a clearance. He was unable to contribute directly to the project to realize his idea. In April 1959, Gould and TRG started patenting the technology that Gould had developed by Schlosser and Townes, filed for a laser patent in 1958, which they were granted a patent in 22nd of 1960. Now, I'm going to be honest with this started was really interesting, but then I got a bit confused, and I think maybe you got a bit confused about what actually happened here. My general understanding is that, yeah, from what I've read here, is that Gould came up with the idea, and it wasn't stolen from him in the same way that other ideas were stolen. He just said, yeah, guess what? You're not allowed to actually work on this idea because the military are going to take control of this idea. Which is like, let's point out for a second, guys, how crap that is that you come up with an idea and then other people get to do it. It's like if you came up with this awesome idea for a book, and it's like, that's a great idea for a book, but you're not allowed to write that book. You know, we're going to get this other author to do it. And then it looks like that idea was also then further stolen, like, by a patent office. So yeah. It's like the same as the engine that runs on water. It was confiscated by the government. Yeah, it's kind of like I think the idea is like, if you think about a laser, it's like, oh man, you can shoot a high power energy beam from one location to another location. Yeah, I can see why the military would want to get their hands on it. But I can also see how stupid it is in the military. If I was the military, I'd be like, I want the person that came up with this to build it. I don't want to get these random other scientists that have never seen it before. I think that's a bit stupid, but you know, what do I know? I care a fair bit about lasers because this is going to sound my chemistry project was actually involved with lasers. Was in the laser lab. My job was trying to look at how lasers could be used to look at the surface of a liquid rather than look at the whole liquid itself. That was my research project, but I was not a PhD. I was just doing a master's of it. And it was still really interesting. I wasn't using like a crazy high powerful laser, but I still was using, you know, a pretty good laser. I think though, to be honest with you, that I was using that laser in 2008. I think the laser that I was using in 2008, you could probably buy now for the same price for like, you know, for like $20 or something. So it's kind of, yeah, times go on and they get better and better and better. So it's kind of one of those things is like technology always keeps on improving. But yeah, so I've always got a soft spot for lasers and light and chemistry in that way. But you know, we could talk about that later on. Today, what we're talking about is Newton's third law. We will explore Newton's third law. This is off the back of talking about the first law and the second law. Let's just talk about those really quickly. First law was what we started off last week. A force is either a push or a pull. Newton's first law: an object in motion will stay in motion. An object at rest will stay at rest unless acted on by an unbalanced force. So that means an object will keep moving unless you stop it, and an object that stops won't move unless you push it. Sort of pretty much that. We went through some examples. Essentially really talking about inertia. Inertia is this tendency for objects to just not want to change. If they're moving, they just don't want to stop. And so some things have high inertia, meaning that they really don't want to slow down or they really don't want to speed up. And some have small inertia, which means it doesn't take much to speed them up or stop them. We talked about seatbelts and why they're really good. And then that was about it. Then Newton's second law, we said, is force times mass. Force equals mass times acceleration. Obviously, the more massive something is, the more force you're going to need to get to accelerate it. If you want to move a heavy bookcase or a brick, you're going to need to apply a lot more force than if you wanted to just move like a soccer ball or a tennis ball. Those things are really, really light. They have low masses, so they accelerate really quickly. We did some calculations on that, and we briefly talked about, well, what is this force called gravity? We call force gravity is an acceleration towards the ground. We said that, well, we give this force a name, call it weight. So force equals mass times g. G is gravity, and on Earth it is 9.8. That means, but we're going to not use 9.8 because we're just going to be in 10. We're just going to use 10. So 10 meters per second squared downward. So that's our acceleration by gravity, which allows us to easily calculate the force of an object on the planet. Mass, of course, it gives us a better idea about what mass is. Mass is, of course, how much matter is in the object. Now, today we're going to talk about Newton's third law, which is the final law, and in many ways, in my personal opinion, it's the most complicated of the laws, but it also is the first law that does something different. If you look at the first two laws, an object in motion will stay in motion, you're talking about just one object. And when you're talking about mass times acceleration, you're talking about just one object. But Newton's third law goes beyond that. It talks about two or more objects, and it talks about how objects might interact with each other with force. And that's what we're going to be discussing. But before we get there, I wanted to talk to you guys about free body diagrams. And I wanted to spend maybe the next couple of minutes talking about what a free body diagram is. Now, Newton's first and second law wouldn't properly be explained if we didn't talk about free body diagrams. If I took an object and I put it on a table and I said, right, there is an unbalanced force, like what forces are acting on this object? Well, we've got a force downwards, we've got a force upwards. And when we talk about an unbalanced force, we need to talk about, well, what does it mean to balance a force? These two forces on this object are balanced. Why are these forces balanced? Because if this is 10 newtons downwards, then this would be 10 newtons upwards. The force on this is balanced because the upward force and the downwards force are equal. One way you could say this is the overall force. The overall force, or what we sometimes refer to as the net force, is equal to 0. Okay? So that's what we mean by saying a balanced force. So an unbalanced force is when the net force is not 0. That would be unbalanced. So what would that look like? Well, that might look like something like this. We have an object. We're just going to draw this object. We're going to represent it as a single point, just because, you know, it's a bit easier. You could draw a box around this object and just pretend that this is the box and this is the center of mass. But yeah, we've got 4 newtons going up and 6 newtons going down. Can someone tell me what is the net force going to be on this object? What do you guys think the net force is if you've got 4 newtons up and 6 newtons down? 2 newtons down. Thank you, Oliver. You're right. It would be 2 newtons down. not only has Oliver's done two things. He's recognized that it's how did Newton get it? Well, what I assume he did is, well, we could do it like this. We're going to call this the net force is the overall force. So to do that, we're going to add all the forces. So to get the net force is equal to adding all forces, which means we could take 4 newtons up and we're going to add -6 for the 6 newtons down. Now you might say, why are we adding -6? The reason we're adding -6 is because it's in the opposite direction. So 4 plus -6 happens to be -2, or 2 newtons downwards. We've got to be careful when we deal with negatives because those two are in the negative direction. Another way you could think about this is you could also think about the 4 newtons getting cancelled out by 4 newtons down with 2 newtons left over. Now this would be a net force. Yes, resultant force would be correct. This would be a net force. The net force is 2 newtons down, so this would accelerate because these forces are unbalanced. How can I tell that they're unbalanced and that unbalanced forces happen? Because this is not 0. Let's do another example, and I would like you guys to copy some of these down as we go. We've got this one here, we've got in green, so I'm going to switch to green. And we've got 6 newtons up and 6 newtons down. Well, for this one, we could do the same thing. The net force is going to be the sum of all the forces. So we've got +6 going up, and we've got negatives plus -6 going downwards. So that's going to be 0. These forces are balanced. And the reason these forces are balanced is because it's the same up and it's the same down. That means that according to Newton's first law, this will stay either at rest or move at a constant velocity. That's one of the ones that I love as students often get confused. It's like, oh, just because the forces are balanced doesn't mean this object isn't moving. This object could be moving. This object could even be falling through the air. It just so happens that the force upwards by air resistance equals that force downwards by gravity. That's what we refer to as terminal velocity. But it doesn't really matter too much as long as you understand that it can move at a constant velocity. So let's compare the two here. For the first one at the start, what we did is he said it's unbalanced because the net force was 2. How do we get that net force? By adding all the forces. This one, the net force came out to be 0. How do we get that net force? By adding all the forces. That means the forces are balanced. You guys ready for example 3, or do you guys want me to slow down a second? Oh, here we go. I'm going too fast. I do record these, but I don't put them up straight away. So that's why I'm trying to slow down a second so you guys can copy them. For example, I've been uploading the engineering maths lessons, but I've only uploaded up to lesson 12, and this is lesson like 16. So what lesson are we up to? So I've only uploaded lesson 12, and this is lesson 14. So it's not a quick process. So you can't really just go, oh, I missed that, I'll go watch it. You've got to keep up to date. Okay, so this next one we're going to talk about, and I'm going to switch to blue, is we've got a net force, but now we've got it happening in more than one direction. So now when we've got multiple forces happening in multiple directions, we've got to start dealing with that. in a year 10 fashion, if I asked you to deal with this, and because you guys are year 10 students, I'm not going to get you guys to do anything too complicated. We just deal with this in two ways. What I would do is I would look at the vertical. So the net force in the vertical is equal to 3 newtons up, or positive 3, plus 3 newtons downward, so plus negative 3, which is going to be 0. And then horizontally, well, we've only got one force acting horizontally. That's easy. We've actually got the net force is 10 newtons to the right. So the overall net force equals 10 newtons to the, whoopsie, not right, left. 10 newtons to the left. That is our net force. This is another example of a unbalanced force because it has got a net force. It's got an overall push to the left. That net force will cause that object to accelerate, and it's going to accelerate at F equals ma, so 10 newtons times the mass times acceleration. That's going to give us our force. Got one more, and that's our red one over here. Hui, this one's got a lot in it. Let's copy this down. Let's deal with our vertical first. Our vertical net force, F net, is going to equal 4 newtons. It's going to be 4 newtons up plus negative 4 newtons down equals 0 newtons. Now, you might say, why we bother? Why don't I just go -4? You might have more than one force. You could have like 4 newtons up and another 6 newtons up over here or something like that. And there are other ways as well that you could end up with a bit of drama. I just thought I would start off by showing you guys that there. What about horizontally? Horizontally, F net, we're going to say we've got 10 newtons to the right plus negative 8 units to the left, or negative 8 because there's 8 units to the left. You could say negative 8 units to the right, but probably wouldn't actually say that. 10 minus 8, which means we've got 2 newtons. That's a positive. So the net force is going to be 2 newtons to the right. That's going to be our net force. Again, this is unbalanced, so this would cause the object to speed up to the right. But yeah, and the only one that was balanced was that green one because the forces were the same. So the reason that I think it's important to talk about this is we keep talking about unbalanced forces. And so what does an unbalanced force look like? This is what an unbalanced force looks like. An unbalanced force is what happens when you've got a greater force in one direction rather than the other directions. I'm going to keep this up for about, I'm going to go quickly fill up my water bowl. I'm going to keep this up for about a minute while I go to get some water. If you guys want to quickly jot this down, copy this down into your books, which you should have been doing as we've been going. There's a pencil there, but you've got about a minute now to do that, or take a quick snapshot of it so you can copy it down later. But yeah, I'll be right back.
I'm just going to put some washing on that. Are there any of your jumpers that I should leave out?
The yellow one
But whatever's in there, so
Okay. I'm back and I've got some more to add. So yeah, free body diagrams. I'm going to give you guys a little bit more practice of these when I give you motion 5. So you will see some of these in motion 5, but yeah, it's just going to be these basic ones. But you might see that these basic ones, why is there a but? I wanted to show you guys just 2 more little ideas here. Okay. I actually could show you 3 ideas. We're not going to do these. I'm going to get you guys to copy these ideas down, but I don't think I'm going to get you guys to actually solve these types of questions when I don't think I'm going to get you guys to solve these types of questions in actual tests, but I want to show you guys just so you can see the reason why I taught you guys the vector stuff at the start. So the net force on this, well, we could actually figure this out easily. The vertical net force equals 4. The horizontal net force is equal to 5. But that's not really very useful because that's not really what the net force is. That's just forces in 2 directions. I want to know what the net force overall is. I want to know what this force here is. That force there is the addition of this horizontal force and this vertical force. That's like saying, what is this force here? What is this net force? Now, you'll notice that for all of these ones here, notice how it's either left, right, up, or down. That's all you're going to be expected to be able to do. But in year 11, if you do physics, you'll be expected to figure something like this out. How would you figure out what the net force is? Well, the net force is going to be, the size of that net force is going to be the square root of 5 squared plus 4 squared. We are going to do Pythagoras theorem here, just like I showed you guys how to resolve 2 vectors. 5 squared plus 4 squared square rooted, which is going to become the square root of 29, which happens to be, no, it's not. No, it's not. The square root of 5 squared plus 4 squared is not the square root of 29. It's the square root of something bigger. 16 plus 25. No, I can't bother to do that. The answer comes out to be 6.4. I mean, that's the size of the net force, but that's not the direction. The direction of this net force is actually going to be whatever this angle is, which is tan inverse tan of 4/5. If I go inverse tan of 4/5, opposite over adjacent, gives me 30, we'll go with 39 degrees. So the net force is 6.4 newtons at 39 degrees from the horizontal. That is a net force that is a bit more complicated because now we've got to deal with angles. We've got to deal with what happens if our force comes off at a different angle. This can be made even harder by doing something like this, where you would have to do that same thing, except you'd have to go, oh, well, this is going to become 3 newtons vertical, because 4 take away 1 is 3, and 3 newtons up, 4 newtons to the right. So then, and then you could then use the same way to find the net force. And then, just because I want to show you guys how the worst way you could possibly get these, the worst way they start to do them, and I just gave this question to my I gave this question to my physics students, is a question, my year 11 physics students, is one that looked like this. So there was like 12 newtons down, 8 newtons to the left, 10 newtons to the right, and then 10 newtons, but at an angle. So that one would be really complicated to deal with. You would have to turn this into a vertical and a horizontal force first, then do this, and then do this. Am I going to get you to do that? No, of course not. I'm not even going to get you to do anything on this page. Why did I get you to copy this down? Because I know that there is probably 1 or 2 students in the class here that I'm like, oh yeah, that makes sense. That's really good. That's you. If you're like that, I reckon I sort of understand what's going on here. Then that means you've actually got that next level. You've got that next level of being able to think here. And this is why we do free body diagrams. I think a lot of people look at these free body diagrams here and they sort of think to themselves, oh my God, sir, I can figure these out. I don't need to draw these pictures. But hopefully now you can see, oh yeah, maybe those pictures are useful for a reason. Maybe it makes sense to start to draw these things out and then try to maybe put them together at the end. So that's sort of what an advanced resultant force looks like. Just wanted to give you guys a brief insight into that. But I think we've been talking about resultant forces long enough. I think it's time for us to get stuck into why we came to this lesson in the first place, Newton's third law. And the other reason why I wanted to talk about resultant forces and overall forces, because it helps us, it's going to help us because we're going to have to be able to draw diagrams to deal with Newton's third law. Well, let's put Newton's third law up. This is Newton's third law, and it is pretty jam-packed with a lot of text here, but I wanted to give you the full law, and then I wanted to break it down later. Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. This is a horrible way of writing down Newton's third law because you're using the word first, second, and exerts and stuff like that. But this is the technical way to write down Newton's third law. The shorthand way that we usually write down Newton's third law is like this. For every action, there is an equal and opposite reaction. Even for you guys looking at that, you still might not know what that means. So let's use an example. If I push against the wall, so I apply a force and I exert that force on the wall, and I push that wall backwards. Okay, I'm pushing that wall backwards. I'm pushing that wall away. I'm pushing that wall away from me. That's what I'm doing. I'm pushing the wall away from me. If I apply that force, there is an equal force in the opposite direction. If I push that wall backwards, if I push that wall, away from me, then that wall is going to push against me. The wall is going to push against me with the same force that I push into the wall. So if I push against the wall with 100 newtons, the wall is going to push back on me with 100 newtons. If I push on the floor with 150 newtons, the floor is going to push up on me with 150 newtons. Every time there is a force, there is an equal and opposite force. It's in the opposite direction too. So if I push forwards on the wall is going to push backwards on me. If I pull on the wall will pull on me. Same scenario here. Every force has an opposite force. Now that we're going to spend the rest of this lesson sort of picking apart this law, sort of really kind of diving into it and just sort of like really exploring what this law kind of means. So let's talk now about an example. So this is my example here. Can someone tell me if I had a magnet and a paperclip set up in this way, can someone straight away tell me what's going to happen? What's going to be the first thing that occurs in this situation? Putting in chat, what's going to happen? The pin will be drawn towards the magnet. Correct. Someone has just said that privately in case you're like, well, I didn't say anything. So the pin is going to experience a force towards the magnet. Now here's the thing, right? That force is going to pull that paperclip towards that magnet. But if that paperclip is experiencing a force towards the magnet, then that means there needs to be another force. If we call this the action, there needs to be a reaction. The reaction is done on the second object, and it moves in the opposite direction. So instead of moving up and to the left, it's going to move down to the right. And that is going to be the same force. For every action, there is an equal, so it's going to be the same size, and opposite, because it's going in the opposite direction, reaction. What's really important is that it's on a different object. So those two forces will pull those two things together. The magnet might not move as much as the paperclip, but they both still will experience a force. And this occurs no matter what. But this is where, and I like to draw this point here, this is where, when I was in year 10, I had a bit of an issue. And I started to think about this, and like, it's actually a common question. It's like, okay, if I push on a wall, the wall pushes on me. Yeah, it makes sense. Those forces cancel out, so therefore there's no movement of either of us. But then I used to get confused. I'm like, okay, then how the heck does anything happen? If I hit a ball, and this is what I mean, how does a skateboard move forward? If I push back, if I push on the ground to be pushed forward, doesn't the ground push backwards on me? And so therefore I shouldn't move. If I hit a baseball bat, why does the baseball bat not fly off with the same force that the ball flies off? Was always like, that doesn't make sense. I never used to understand, because I was like, oh, well, if this applies a force to the ball, then there should be an equal force on the bat. The ball goes flying off really, really quickly. It shoots off. So why is the bat not shooting backwards with just as much force? That used to confuse me. If I think about a bicycle, if I'm pushing down on the wheels, how can I actually push the pedals downwards if the pedals are pushing up with the same force? I was like, how can you move? It doesn't make sense. And so that's why I think it's important to talk about Newton's third law in a second way, and to really outline this. And this is the same thing. I would love you guys to copy this down. Redefining Newton's third law. When two objects interact with one another, there is an equal force. That is true. But the force is experienced by both objects. The objects accelerate differently. And that's one of the words that I think is depending on their mass and other forces. I'm going to get you guys to copy this down first, then I'm going to explain what that means. So what does it mean? Okay, so let's grab a look, and the best example that I've seen time and time again, and the reason I use this example is because so many people get confused by it, is to talk about an astronaut. This astronaut and the Earth. Now this astronaut feels a gravitational pull towards the Earth. That's going to be a force. The astronaut's going to feel this gravitational pull towards the Earth. At the same time, every force must have an equal and opposite reaction force. So therefore, the Earth must feel a force pulling it up towards the astronaut. And I'll be like, what? Really? And I'm like, yeah, there is going to be a force. Not only is that force going to be pulled up towards the astronaut, guess what? It's the same size. Now you might be like, okay, how is that possible? Because honestly, we don't see the Earth shaking every time an astronaut goes on a spacewalk in space. So what's going on with these forces? Yes, these forces are the same, but there's one key difference. The way to understand Newton's third law best is to actually go back to look at Newton's second law. Again, F equals ma. So how do I do this? Well, let's say if both the astronaut, let's do this, and the best way I usually do this is with pictures. It's a bit weird, but I do it with pictures. If the astronaut and the Earth experience the same force, right? Well, what's the difference? The difference is that for the astronaut, he has a mass that's, roughly, it's not too big. It's not too big. So therefore, the mass divided by the force by the mass is going to give you an acceleration. Yep, that makes sense because it's force divided by mass is acceleration, and F equals ma. They experience the same. Feel like his mass is maybe, I don't know, let's say like he's got a spacesuit on, so maybe let's say it's 150 kilos. You could get an acceleration of about maybe, let's say that the force pulling him downwards was say 1,500. You would get an acceleration of about 10. That seems pretty logical. But if I look at using that same force, that same 1,500 newtons, let's apply that to the mass of the Earth. Now, the mass of the Earth is huge. It's massive. It's astronomical. It's a 9 followed by 30 zeros. That's how many kilograms it is. That's how big it is. So in comparison, it's going to be a massive, massive, massive mass. It's going to be huge. That's going to be such a massive number. I can't even fit it all on this page. As I said, it's going to be huge. So that means if you take a regular number, like 1,500, you divide it by a massive number, the acceleration that comes out at the end is going to be tiny. It's going to be super small. And therefore, it's barely going to be noticeable. With the case of the acceleration, it's going to be barely noticeable. So what I usually say to this is, yes, both objects will experience the same force. Well, both objects will have the same force act on them, but they will experience it differently. When I say experience, I mean they will accelerate differently because of their mass. They will also experience differently depending on their force. If they have other forces acting on it, that might dampen the acceleration. So let's go back and let's revisit some of those slides I was just showing you. Like, let's look at this slide here. I said that they're both going to experience the same force. But because the weight of the magnet is heavy, it'll experience a low acceleration, whereas the paperclip is light, so it will experience a high acceleration. So even though there is the equal force, it's going to not look like the same acceleration because the magnet is going to accelerate really quickly and fly towards the magnet. Even though that magnet does experience a force and that magnet will accelerate, it's not nearly going to accelerate as much as that paper. The skateboard is another example. Even though you and the body, let's just say your body plus a skateboard, let's say that's 90 kilograms, that's going to experience this action force. The reaction force is on the earth, and the earth is not going to move nearly as much because even though it's the same force, the earth has a different mass. The last example is the baseball bat and the baseball. The baseball has a very low mass. So because it has a low mass, it has a high acceleration, whereas the bat has a higher mass. So therefore it has a lower acceleration. Not only that, but the bat is also attached to a person. That person is going to be doing more than just swinging the bat. They're going to have their own mass, and that mass is going to add. They're going to have their own mass, and that mass is going to add to the mass of the bat. Plus, they're going to be standing. They're going to be standing, and this is not going to work at all. But I'm just going to do this. We're going to pretend this person is going to be standing on the earth, and therefore there's going to be a force by the earth. If you get forced downwards, the earth's going to push back up and cancel that force a little bit because it's going to change the acceleration. So yeah, you're going to have to try to move not only the mass of the object, but also the mass of the earth, as long as you're holding it correctly. So yeah, that's all going to add to the mass, which stops the bat flying backwards. There will still be a force, like you will feel the bat want to move backwards, but as long as you're standing correctly. It's the same sort of, if you're standing on roller skates and you throw a basketball, you will actually end up moving backwards because you push the basketball forwards with a force, so the basketball will in turn push you backwards with a force. But if you're standing on roller skates, you should expect to move backwards just a little bit. And the same thing would occur if you were in a shopping cart or if you were on a skateboard. So yeah, these are just different ways that you can, this is the reason why, yeah, sure, it's the same force, but because the masses are different and there are other forces at play, it does not mean that it's the same acceleration. There is the same acceleration if you're dealing with like pool balls. So pool balls, because they're all the same mass, you usually see them when you collide two pool balls, they'll both fly off in different directions at the same speed, or they'll collide and bounce off at the same speed and the same acceleration. And that's because they've all got roughly the same mass. Now, before I move on, are there any questions about what I've explained here? Any queries? Any being like, whoa, what? Right, time to test you then. Let's go have a look at these pictures. Well, this isn't a test yet, but these are just some more pictures. If you look at a rocket, when a rocket shoots forwards, we say that it shoots a bunch of gas out. And that gas that comes out, if it pushes backwards on the gas is going to push the rocket forwards. This is the same thing that causes a plane, the engine in a plane. This is a bad picture of a plane. It looks like that roughly, and then you've got the wing coming out like this. What it does is it takes the air and it pushes the air backwards. And because the engine of the plane pushes the air backwards, that in turn causes the plane to move forwards. Another example, propeller on a boat. Propeller on a boat pushes that pushes the water backwards, and the water being pushed backwards, the action force forces the boat to be pushed forwards. And again, you've got the Newton's cradle, which is always a great example, as the force pushes the force gets pushed along this sort of along the balls here. I actually don't like Newton's. I don't like Newton's cradle here. I'm sure we're going to take that picture out. But yeah, these are some more examples of Newton's forces here acting to push an object forward. I like this one of the dog. It's the same as the propeller, but if that dog kicks the water backwards, what that does is it will move the dog forwards, because you can think about these as the action-reaction pairs. If this is an action, then the reaction will be the same force on a different object, pushing that object forwards. This is, by the way, how I find something called, I wonder if I talk, let me just give me a second, sorry. Yeah, I don't actually talk about it, so I'm going to talk about it here. This is how I find something called action-reaction pairs. And I'd like you to write this down. I know this is no pencil here, but I would like you to write this down. Action-reaction pairs. What are action-reaction pairs? They are two forces that are the same size in opposite directions on different objects. I might talk about these a little bit more detail next lesson, but this one, the bottom, is what gets people. So in this case, these are action-reaction pairs. They're the same force, they're in opposite directions, one's backwards and one's forwards, and they're on different objects. One's acting on the water and one is acting on the dog. You guys might experience this next time you're at a pool, which who knows when that's going to be because of COVID, but next time you're at a pool, think about it. The way that you go forwards is not by pulling the water. The way that you go forwards is by pushing water backwards. The faster you push the water backwards, the more the water will push you forwards. Now here's the question for today. I've got two examples. Then am I going to do that stuff? What time have we got? Probably not, I don't think. Let's talk about these two examples. And then that should get us close enough to the end of the lesson that I can just say, yep, we're done. So let's talk about this first example here. While driving down the road, a firefly strikes the windshield of the bus. So a small fly hits the windshield of the bus and makes an obvious mess in front of the face of the bus driver because it's got gunk all over it. This is the case in Newton's third law. The firefly hits the bus and the bus hits the firefly. Which of the two forces is greater? Now I want you guys to write down, and don't push enter yet. This is a technique that I've learned from, I think it was Miss Tom sort of explained this, and I kind of like this way of testing you guys. I'd like you guys in chat to write down the answer that you think, but don't push send. So in chat, I want you to write down which of these two will experience the greater force. The firefly or the bus, or something else. So which one's going to experience the greater force? The firefly the bus, or something else, whatever. I want you to write down in chat what you think. I'm going to give you guys 30 seconds. Don't push enter yet though. I'm going to give you guys 30 seconds to write down in chat which one you think is going to experience the greater force, the firefly, the bus, or something else. So 15 more seconds to write it down in chat. So just type it in chat. Don't push enter. Okay. So what we're going to do now is this. In 5 seconds time, what I'm going to get you guys to do is I'm going to get everyone to push send, everyone to push enter at the same time. The advantage of that is if you made a mistake, it'll go past so quickly, I won't even be able to see what you said. So it doesn't matter if you made a mistake. So when I get to 0, when everyone to push send and write down their answer, is that the firefly experiences a greater force, the bus experiences a greater force, or is there something else going on? So then, in ready, in 5, 4, 3, 2, 1, send. Beautiful. I got a couple of answers pop up here. A couple of them privately messaging me, a couple of them more public. That doesn't matter. Let's have a look here. We've got bus, firefly. We've got the same force. We've got firefly, bus, firefly, 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 chicken. Okay. The answer here is exactly what I thought, and the person who got this correct straight away was Elaine. Good job, Elaine. They are the same force. This is a trick question. It makes it look like they are different forces. I mean, look at it. The one of the firefly gets crushed, whereas the bus, well, it's a bus. It's got a really heavy mass. But the trick here is that they are, even though they are the same force, even though they are one gets squashed and one doesn't really feel anything, they're still the same force. Every action has an equal and opposite reaction. This is a trick question. That's why I tried to give you guys a way out. I said, oh, maybe it's something else, because in this case, it is something else. Now, even though they experience the same force, right, we know that the bus has a huge mass. Because the bus has a huge mass, the acceleration is going to be very, very, very small. Whereas the fly has a very, very small mass. And because if you divide by a very small number, you are going to end up with a huge acceleration. And that's why the poor fly gets completely crushed. Now, if you got that wrong, that's okay. I'm going to give you guys another chance to redeem yourself. We're going to do example 2. Now, example 2, we're going to do exactly the same way. This time, though, I'm going to not be mean to you, and I'm going to say these are the 3 options. There is no option D. The answer is one of these 3. It's either A, B, or C. So, many people are familiar with the fact that rifles recoil when fired. If you're not familiar with it, I will tell you what recoil means. Recoil is when you shoot a gun or a rifle and it pushes back into you. Okay, it actually goes a little bit backwards to you. The recoil is a result of the action-reaction force pairs. A gunpowder explosion causes hot gas that expands outward. And that hot gas pushes the bullet forward. But with Newton's third law of motion, the bullet pushes backwards on the rifle as well. So those forces are equal and opposite. The force, if I have a bullet here, the force that pushes the bullet outwards is going to be the same as the force, this is a weird gun, but trust me, that pushes the the gun backwards. So here's the question. Consistent with the motion, the bullet pushes backwards in the rifle. The acceleration of the recoiling rifle is A, B, or C. I want you to write down your answer in chat, but don't push send. So that's a reply. Don't push send. Just write down in chat. Is the acceleration greater on the bullet? A. Is the acceleration of the rifle greater than the acceleration of the bullet? So the rifle accelerates at a higher has a higher acceleration than the bullet. B, the acceleration of the rifle is smaller than the acceleration of the bullet. Or C, the acceleration of the bullet and the rifle are the same. So have a think about that. Put your answer in chat, but don't push enter yet. Okay, going through the answers again, and then we'll get ready to send it. So, they both experience the same force? Is the greater acceleration going to be A on the rifle because it's greater than the bullet? Is the greater acceleration going to be B on the bullet because it's going to be greater acceleration than the rifle? Or C, the acceleration of the bullet and the rifle are the same? Okay, we are going to release the answers. Can I get you to get ready to push enter in 5, 4, 3, 2, 1, go. I want to see a bunch of answers. Okay. All right. Now I'm not going to look at the names here, but I'm going to see we've got BB. We've got a BB, an A, a BBB, B. Yes, the correct answer, ladies and gents, is B. You guys actually did a little bit better than my actual year 11 physics students. This looks like another trick question, but this time the trick question is just because I tried to trick you guys twice. But the trick here is to talk about the acceleration. Yes, they both experience the same force, correct. But the bullet has a small mass, and so therefore will have a large acceleration, whereas the gun has a large mass, so we experience a small acceleration. 1 second, ladies and gents. So you could even just because we can, let's just do some random numbers here. Let's pretend that the force was 1,000 newtons. Well, if we did 1,000 newtons here, let's say that the mass of the bullet was maybe let's say it was like 10 grams. So we'll go 0.01 kilograms. So therefore, 1,000 newtons divided by 0.01, that's going to be the same as 100,000 meters per second squared. And that would be for the bullet. Let's compare that to the rifle. Let's say the rifle, let's make it a heavy rifle. We'll say the rifle is maybe, I don't know how much rifles weigh, so I'm just going to take a guess. We'll go with 10 kilos. No idea, babe. No idea what it is. So if I go, we know it's 1,000 newtons divided by, if I go, remember A equals F divided by M. If I go 1,000 divided by 10, that's only going to accelerate at 100 meters per second squared. We got 100,000 to 100. The bullet is definitely going to be moving at a much higher acceleration. So the rifle has a smaller acceleration, than the bullet. And that's realistically how you can calculate that sort of idea here. And there's actually nothing wrong with doing, by the way, this. If you ever feel like, oh no, I need to do some calculations, I need to do this. If you're more comfortable with dealing with equations, then yeah, sure, put some random ideas in, put some random values in, and see what comes out. It will probably help you understand the answer a little bit better. And that's why I always say, by the way, a very, very small mass, if you divide by a small number, you get a huge acceleration at the end. So that's how you do the second law. What does this have to do with, I wanted to show you guys one last thing. What does this have to do with, what does this really have to do with engineering? Well, one thing we can always do is we can talk a little bit about rockets. Example, Newton's third law at work is in rockets. As the gas escapes and it is forced downwards, the reactionary force in the rocket moves it upwards. Every kind of propulsion, including planes, guns, trains, sure, trains. Every kind of propulsion, sorry, trains aren't the propulsion. Planes, jet propulsion in water as well. All of these relies on this fact. It relies on pushing out something from the bottom. Elon Musk, who we all know, our PayPal fan, has been making reusable rockets, which I kind of think are pretty cool. My wife really doesn't like Elon Musk. She says he's a bit of a jerk, and I'm like, because he's forced his workers to work during COVID and stuff like that. I'm like, whatever. I'm like, I don't really mind. I think he's, even though he's a bit of a jerk and he's a bit up himself, he's like, I'm the God's gift to humanity. I still think he is doing some really good things. I think we won't be able to get to space unless we can reuse the rockets that we send up there. So yeah, like he's been inventing reusable rockets, and what they do is they use the same force. They push downwards to create lift, but they don't try to, when they're coming down, what they do is they've got this force of gravity that's pushing them down, so they try to equate this with an equal thrust force, a force of thrust upwards, and try to balance this out so that it can slowly come down and land safely, not so that it hits the water and crashes. So that's actually kind of interesting too. So that's where that's what the tie in with Newton's third law to engineering.